All right, greetings, scholars. A beautiful mind here. We are moving into chapter 6 on exponential and logarithmic functions. We're going to start off with section 6.1 exponential functions. A few learning objectives. In this section, you will evaluate exponential functions, find the equation of an exponential function, use compound interest formulas, evaluate exponential functions with base E. So which of the following equations are not exponential functions? So the general form of an exponential function, the difference between an exponential function versus a power function is going to take on the form of like some variable x raised to some power, right? Raised to a power. With the exponential function, the variable is now in the power. The variable is now your exponent, right? So you're going to have some non-negative base that's also not equal to 1 raised to some variable x, right? So which are not exponential? So notice in the first one, our x is in the power. So the second one, that's a power function. I know these sound a little bit recursive, but your x is the base, so that's not an exponential function. With an exponential function, again, your variable x is the exponent. I think that's the only one. It looks like G is the only one. Wait a minute. Also with J, notice that base is negative. So a negative base is not indicative of an exponential function. So J is not exponential as well. Okay, I think the rest of them are good to go. So G and J. Yeah. So given this f of x, evaluate f of 2 without using a calculator. Okay. So our given f of x is 5 times 3 to the power of x plus 1. And we're asked to evaluate f of 2 without a calculator. So 5 times 3 to the power of 2 plus 1. Okay. So that's 5 times 3 to the power of 3. 3 times 3 is 9, times 3 is what, 27? So 5 times 27. That's what, 100 plus 35? 135? Okay, so we got a bunch of extra space, but that's okay. All right, so let's see. At the beginning of this section, we learned that the population of India was about 1.25 billion in the year 2013 with an annual growth rate of about 1.2%. This situation is represented by the growth function given, where t is the number of years since 2013. To the nearest thousand, what will the population of India be in 2031? Okay. So we're given this model where it tells us the population based on time, where we have 1.25 times 1.012 to the power of t. Okay. So if we let the year 2013 be year 0, right? We're going to let the year 2013 be when time is 0, and I'm putting in parentheses that this is 2013. The population, well, I guess we got that already. So we don't really need that. But we can use that we're setting the year 2013 to year 0. We want to find out what's going to be the population in the year 2031, right? So if 2013 is the year 0, then how many years later is it until 2031? Let me see. If that were 20, that would be 11 plus 7. Looks like it's 18. So it looks like the question is asking what's going to be the population 18 years later. All right. Again, that should be 2031. All right. Okay. I'm sorry, my table is just driving me nuts. I don't know. I gotta find another table. I'll work over here. Oof. It's like, if I like move just a little bit, it's like creaking and cracking, and I'm like, yo, will you please stop that? All right. So we want to find the population at 18 years later. Let's see. So we have this 1.25 times 1.012 to the power of 18. I'm just going to use my calculator. This one. I think I'm going to put it into my y equals 1.25. There it is. Okay. No. Okay. So we're going to say 1.25 parentheses 1.012 to the power of x. That should be good. Then I'm going to call on the function. I want to evaluate this function when x is 18. So 1.55 billion approximately. 1,000. So that's what, 3 decimal places? 1.549. I said peoples. People. All right. That's correct. Based on that model. Okay, I'll let you read through this. Given 2 data points, how to write an exponential model. I'm just going to kind of wing it. Like I feel like I'll do better with just winging it. So in 2006, 80 deer were introduced into a wildlife refuge. By 2012, the population had grown to 180 deer. The population was growing exponentially. Write an exponential function representing the population of deer over time. Okay, so the general model for an exponential, I'm going to use P of t, P naught times e to the kt if it's exponential growth. I'm going to glance. I wasn't going to do it before. Yeah, I think this is good. Now I'm using base e. I think they're using a different model. Let me see. Deer were introduced into a wild. Let me. I want to do it this way first and see what result I can get, and then if this doesn't work, I have another model that we can use. The growth rate. Let me see. In 2006, 80 deer were introduced. By 2012, it had grown to 180 deer. So we do have 2 pieces of information. Again, we're going to let the year 2006 be year 0. So when time is 0, it's at 80. And then 2012 is what, 6 years later? It's at 180 deer, right? So if we let t be 0, all right, then long story short, our initial population is 80, all right? And that's not too bad, okay? So then let's let t be 6. So now if we let p not be 80, we'll have 80 e, we're trying to solve for the growth rate. The time has been 6 years, and the result there is 180, right? So let's see if we can solve for the rate. Now again, this might not be the right model. This is how I usually do them, but they might use a different model. So if it's not the right model, we'll come back. So we're trying to solve for k. We're going to divide both sides by 80. We got this e to the k, or I guess you could say 6k. All right. Equals 18 over 8, 9 over 4. So 180 divided by 80 reduces down to 9 over 4. Now, I guess I am kind of jumping the gun a little bit because we definitely haven't talked about this. Okay. Because we haven't talked about exponential and some operations there, I'm going to backtrack to this other model I think we should use. Yeah, I think it'll be okay. We could keep going. Like, what we're doing is not wrong, but we just haven't talked about it yet. So I'm going to backtrack. Let me get rid of this. And I'm going to change the model. Whoops. I saw something that was like, and here I'll do it so you can see what I've changed. A times b to the power of x. So that seems like the model like they were using. And we should probably do like n of t. Let me try to use the proper form. So then n of t to the power of t, right? Okay, now we can still kind of proceed, we can still proceed in the manner that we were. If we let t be 0, then b to the power of 0 is a 1, and there's an equal sign in there. Right there. Okay. So again, if we let t be 0, that means that a is going to equal 80. Okay. So then we have 80 times, that's fine, b to the power of, now we're letting t be 6, and the output is 180. Okay. So then b to the power of 6 equals, I think that was the 9 over 4 that we had. So we should take the 6th root on both sides. Let me see. And because it's an even root, we really should do plus or minus, but we don't use the negative for a base of an exponent, so we're just going to take the positive. It should be the 6th root of 9 over 4, whatever that number is. So one way we can do that in the calculator, we can say 9 over 4 to the power of 1 over 6. Okay. Let's use 1.145. So b is approximately 1.145. Okay. So then the number of deer in our population based on time looks like it's going to take on the form 80 times 1.145 to the power of t. Okay, and we can just confirm that our numbers work in this. So like, for instance, when t is 0, we get our 80, and then when t is 6, we should get 180, right? Or something close. Okay, I feel good about this. Let's see, how do we do? 1.1, yeah, we put 1.145, that's fine. Okay. So unless otherwise stated, do not round any intermediate calculations, then round the final answer to 4 places for the remainder of this section. Okay. The exponential model for the population of deer, that's exactly what we have. So I think we're good. Okay. So find an exponential function that passes through these points. Okay, so we're essentially doing the same thing that we just did. This one's a little different though because they didn't give us the initial. They didn't give us when t was 0 or when x is 0. But it's going to take on the form. We can use the same model. So let me see. F of x equals a times b to the power of x. Okay. So then we're going to plug in the information we're given. So the first piece is when x is -2, y is 6. So a times b to the -2, the corresponding y is 6. Okay. All right, I'm actually gonna go ahead and solve for a from here. Now that negative power is the same as what? A over b squared equals 6. So then a equals 6b squared, right? Okay, and then the second piece of information we're given, when x is 2, y is 1. And let me see, so ab, when x is 2, the corresponding y is 1. We have an expression for a, so we're just going to substitute that in. So then we have 6b squared times b squared equals 1. Okay. So then b to the 4 equals 1 over 6. So then we take the fourth root on both sides. Again, normally whenever we take an even root, we do plus or minus. But because we're working with exponential, a negative base for your exponent, for your exponential doesn't make sense. So we just take the positive. So then b equals the fourth root of 1 over 6. So then our function takes on the form. We need to go back and solve for a. Let's see, that's to the power. So that's to the power of a half. So then a takes on the form 6 times 1 over 6 to the power of a half. Okay, let me keep working on the side over here. That's going to be the same as 6 times 6 to the -1/2. So I think we can add those powers. So 1 plus a -1/2 is 6 to the 1/2, whatever the square root of 6 is. Okay. Let me see. The square root of 4 is 2, and the square root of 9, so it's like 2 point something, right? So we're going to say 6 to the power of a half. Okay. So for a, we get approximately, now we said 4 decimal places, 4495. And then for b, we get the fourth root of 1 over 6. So we can say 1 over 6 to the power of 1 over 4. Whoops. 4 decimal places, 6389. Okay. So then our function takes on the form of this 2.4495 times this 0.6389 to the power of x. Okay. So then let's check this before we go forward. I'm gonna say 2.4495 parentheses 0.6389 to the power of x. Close the parentheses. That should be fine. And then I want to evaluate that. Let me see. When x is -2, we should get something close to 6. Okay, that's close enough for me. And then when x is +2, we should get something close to 1. And that's close enough for me. Okay. Let me see. Because we don't have the initial value, we substitute both points into an equation of this form, then solve the system for A and B. Okay. So it looks like they pretty much did the same thing we did. 2.4492. Okay, that's fine. We're close enough. Oh, it looks like they rounded. The reason the numbers are a little bit different because we're rounding at different places. Like, they got that 6b squared, and so they plugged in that 0.6389. I think I plugged in an exact result. That's why the numbers are a little bit different, but it's fine. It's close enough. And here's a pictorial representation. Okay. Do 2 points always determine a unique exponential function? I feel like that's a yes. Let's see. So provided the 2 points are either both above the x. Oh, that's interesting. Yes, provided the 2 points are either both above the x-axis or both below the x-axis and have different x-coordinates. But keep in mind that we also need to know that the graph is in fact an exponential function. Not every graph that looks exponential is really exponential. We need to know the graph is based on a model that shows the same percentage growth with each unit increase in x, which in many real-world cases involves time. Given the graph of an exponential function, how to write its equation? It's kind of a repeat of what we were just doing. You can find 2 points on the graph, then from there, once you find 2 points on the graph, it's kind of a repeat of what we just did before. So find an equation for this exponential function. Let me see. We have the point when x is 0 and maybe when x is 1. Right? Those look like fairly simple points to use. Okay. So we're gonna have the model take on the form similar to what we had before. We'll say f of x equals a times b to the power of x. And we're going to use the points when x is 0, it looks like the corresponding y is 3. And when x is 1, the corresponding y looks like it's 6. Okay. So then if when x is 0, that means that a has to be 3. Okay. And then let's put this together. So then we have 3. We're still trying to solve for b. Now when x is a 1, I'm not going to write it because b to the power nothing, or there's an implied 1 there, should I say. But anyway, so b to the power of 1 equals the corresponding y is 6. So then we divide both sides by 3. It looks like b is 2. Okay. So it looks like our function takes on the form 3 times 2 to the power of x. And again, we can check, right? When x is 0, we get 3. When x is 1, we get 6. So, right? That's 3 times 2 is 6. I think that's pretty good. Oh, they use 212. We got the same thing. Okay. Given 2 points on the curve of an exponential function, how to use a graphing calculator to find the equation? Press stat, clear any existing entries in L1 and 2. In L1, enter the x, and L2, enter the y. Press stat again, cursor over to calculate an exponential regression, and displays the values of a and b. Okay. Use the graphing calculator to find the exponential equation that indicates these points. Okay, let's give it a go. I think that'll be fun. If we can get our calculator to behave. There we go. I'm going to clear all this out. Now, if I hit stat, edit, okay, so it's already clear. So it said you can put those values, the x's. So we have 2 and 5. And then the corresponding y's, we have 24.8. And 198.4, 198.4, okay. Now I'm gonna go back to stat and go over to calculate. I think it's number 8, quadratic. Exponential regression, number 0. Stat. Let me just hit enter. Okay. So again, if we're using the model f of x equals a times b to the power of x, it looks like our a from the calculator is 6.2 and our b is 2. So we're saying that f of x takes on the form 6.2 times 2 to the power of x. That was interesting. Okay, let's see. Yeah, 6.2 times 2 to the power of x, yeah. That was interesting. Let me see, the compound interest formula can be calculated using this, okay. So I'm making this recording right after lunch, and I think I have a case of the itis going on. Because I am like extra sleepy out of nowhere. I thought I had the energy to do it, and then I got to whatever slide this is, and I'm like, okay, I want to go to sleep now. Let me see. So I'll go through the details of this when I work an example. Okay, so we invest $3,000 in an investment account, paying 3% interest, compounded quarterly. How much will the account be worth in 10 years? Okay, so compound interest. Let me see. So the future amount is going to be P times 1 plus R over N to the power of NT. That's our compound interest formula. Let's plug in what's given. So we start with $3,000. That's our P, our principal. 1 plus the rate is 3% as a decimal, so 0.03, right? 3%, we have to convert it to a decimal. So N is our number of compoundings per year, or in other words, how many times the interest is applied in a year. So if it's applied quarterly, that means 4 times in a year. And after 10 years, our time is 10 years. Okay. So then with that, we just use our calculator. Let's see. So we got 3,000. 1 plus 3% divided by 4 to the power of 4 times 10, or we can just say 40. After 10 years, only $1,000? Yeesh. So it looks like this is approximately 4,045 and 5 cents. And again, this is the, can I move that? Oh, it's totally in my way. Let me just move it over here. This is the amount in the account after 10 years. Oh. Okay, this is exactly what we got. Okay. We're almost there. 3/4 of the way there. Let me see. 529 plane is a plan. A 529 plan is a college savings plan that allows relatives to invest money to pay for a child's future college tuition. The account grows tax-free. Lily wants to set up a 529 account for her new granddaughter and wants the account to grow to over $40,000 over 18 years. She believes the account will earn 6% compounded semi-annually, twice a year. To the nearest dollar, how much will Lily need to invest in the account now? Okay. So it sounds like we're still using our compound interest formula. The future amount, A of t, equals P times 1 plus R over N to the power of NT. Okay, we're trying to solve for P. So we're going to plug in what's given. So again, we're trying to solve for P. 1 plus the rate was 6%. So that's going to be 0.06. I think it was compounding semi-annually, which means twice a year. So that means our N is 2. 2 times, I think it's 18 years. And we want this amount to be larger than 40,000. Right. So now we just have P times some number. The number is not going to be negative. So then P needs to be greater than whatever 40,000 divided by that number is. All right, 40,000 divided by this number. So as long as P is, we deposit over whatever that number is, then in 18 years with this account, she should have over 40,000. One, 2, 3 divided by, we got 1 plus 0.06 divided by 2. Okay. And I'm actually going to insert another set of parentheses right here. So then we can say that to the power of 36. So almost 14,000. This is approximately $13,801.30. Okay, so as long as our account is greater than or equal to that amount when she starts, by the time the granddaughter for her child, by the time her child is ready for college in 18 years, then, wait a minute, they don't know what, 40,000? I don't know what school you go to. School's expensive. That's not, I mean, yeah, I don't know. School tuition definitely costs more than that, but that's still something good to have, because then it's like, okay, if you have this egg ready to go, and if they're able to generate a scholarship, then like if it were me and I had something like that or higher, and my child was, I was about to say my student, could get a scholarship, if they can like fund it and graduate, if they like, to me, if they were to graduate, you know, on the least amount of money, I would give them that once they started working. Like they would have to like graduate from school, if they're going to go to grad school or whatever it is they're going to do, finish school and be working someplace for at least 2 years. Then I would release the funds to them and they can use it for whatever they feel like they need to. Dang, now this is making me thinking of like another content creator on YouTube. His name, his channel, his organization is called Forbidden Knowledge, and his name is Billy Carson, and he was talking about, you know, protecting the funds and the resources for the future generations over time. Because if you just give them to money, it's going to get squandered. But you got to make them work for it, make them be established and be responsible and prove themselves. Like you had to have some kind of stipulation. I thought it was a really good idea. Don't just give it to them, because anybody in their right mind, they're just going to take it and do whatever. They might blow it and then they're gonna, all that time could just go to waste. Versus you make them work for it, like they have to be some kind of conditions, constructive conditions, so that way when they gain access to it, they could be more responsible with it. I just think that's a good idea. I feel like at some point, we kind of have to start thinking like this. We don't have to, but I think it's a good idea. I know that I feel like somebody has kind of done like that for me, and I would want to just pay it forward. Like, okay, can I? How many people can I create this thing for? You know what I mean? In the future. 13,801. Mm-hmm. Okay. So here we go. This is what I was trying to do earlier. The letter E represents the irrational number 1 plus 1 over n to the power of n as n increases without bound. So as n goes off to positive infinity, this expression approaches the number E. E is a number similar to pi, where it's like 2.73 something. But we have this expression for E because, well, it has this unique property that comes out in calculus. The letter E is used as a base for many real-world exponential models. To work with base E, we use the approximation 2.718282. The constant was named by the Swiss mathematician Leonhard Euler, who first investigated and discovered many of its properties. Okay. Calculate this, round to 5 decimal places. So I would just use the calculator. E to the power of 3.14. Two, 4, so 8, 7. 10, 38, 7. Okay. Okay. So I think that was really just like to see if you know how to use your calculator. I'm just using the one that you see me using just for instructional purposes. You might have this one, you might not. So if you don't have this one, then you have to try to figure out on whatever device you have. Because, everybody can have all sorts of different calculators. All right. So for all real numbers T and all positive numbers A and R, continuous growth or decay is represented by this formula. And see, that's what you saw me using earlier. I call this like the PERT formula. I'm used to seeing it like in continuous compound interest. A equals P e to the RT. Okay. Yeah, you see it kind of at the bottom there. Okay, let's see it in action. So given the initial value, rate of growth or decay, and the time t, how to solve a continuous growth or decay function. I'm going to let you read through this on your own, and I'm just going to kind of like explain it as I go. So a person invested $1,000 into an account earning a nominal 10% per year compounded continuously. How much was in the account at the end of 1 year? All right. So whenever you see continuous compound compound interest, the way I remember that one is PERT, right? So that's like A equals P e to the RT, okay? So at the end of 1 year, so we want the amount in the account after 1 year. We're starting with $1,000. E to the rate is 10%, that is massive, and the time is 1, okay? So 1,000 times E, 10% is 0.1. I think that's it. 1,000 times E to the power of 0.1. Ugh. $11.05 and 17 cents. That's correct. We might have one more. It says radon 222 decays at a continuous rate of 17.3% per day. How much will 100 milligrams of radon 22 decay to in 3 days? Okay. So if we're doing exponential decay, it's still PERT, but instead of RT is negative. I think it's negative RT for exponential decay. Okay, we're still trying to find a future amount after 3 days. I want to say this is usually based on years, so we might need to do a conversion. We might need to convert days to years. Let me think about it. Can we just let that be days? Will that work? Normally time is in years. Let me see if we can just leave it. I think we can. Okay. So then we're saying the amount that remains after 3 days. How much are we starting with? Okay. Let me think. Oh, there it is. 100 milligrams. E to the rate. Okay, if that's 17.3%, so it should be a negative 0.173 times 3. And I think we just use the calculator from there. So 100 times E, negative 0.173 times 3. It's approximately, that's a lot. It seems like it's decaying. 59 point, we'll say 5115 milligrams. Seems like it's decaying rapidly. I guess it would taper. Oh, wait a minute. I'm sorry. Well, I guess we're wrapping up. Let me just try to wrap it up. That's correct. And that brings us to the end. My dehumidifier just kicked on. So with that, we're going to go ahead and end the session here. And from one beautiful mind to another, enjoy the rest of your day. Take care. Peace.